one of my colleagues, Tom Schutt, from the astrophysics and particle astrophysics group here. Tom got his PhD from Berkeley in 1993, and in the early 90s, he participated in some of the pioneering efforts to discover the identity of the dark matter of the universe. And he's been working on it ever since. He went to Princeton. There he investigated atomic xenon as a great element to capture dark matter. And through his efforts and various collaborations that he's been in, this has now become a very important technology in the search. He went off to a professorship at Case Western Reserve, where he worked with Dan Akerib on one of the largest xenon detectors of dark matter, the Lux experiment. And very recently, Dan and Tom came here to work with SLAC in scaling this up to what really we hope will be the ultimate detector of dark matter. So he's going to tell you the story tonight. Why we know there's dark matter, where it comes from, what it might be, how we might find it. The story isn't over, but that part of the story that we know about, you'll hear tonight. So, thank you very much.
Thank you, Michael. And it's a pleasure to be here to tell you about this, I think, really interesting story, looking for dark matter. The story starts, well, one of them started way back at the beginning, with Newton, who sort of gave birth to physics. And yes, there's an equation. It's the only equation in the talk. I figure most of you probably have seen this in high school, right? This is the force of gravity, say with the Earth, and something that would orbit the Earth, and the distance from the center of the Earth to the thing. And then on this side is I shouldn't call it this, but the centrifugal force, the tendency of the body to move straight. And this is a nice, interesting thing. Back in Newton, this is from Poughkeepsie. He has this nice little diagram. He imagines throwing a ball, throwing it harder still, and then doing that on a mountain. And if you throw it at the right distance, at the right speed, determined by this velocity, this equation then tells you that the thing can be perfectly balanced and it'll go in an orbit. Okay? I like to think of this as weighing the Earth. The little mass on either side drops out, and I can rearrange this equation once someone measures G, which happened at some point. If you know V and R, you measured the mass of the Earth. So Newton in the 1670s came up with equations with the Earth. Can I put it on a scale? And the answer is no, of course not.
Okay, everyone. Today is my SLAC lecture. Dr. John-Sik Lee. Dr. John-Sik Lee joined SLAC in 2011. He's now a staff scientist at SSI, or Material Science Division. Dr. Lee got his PhD degree in Pohang University of Science and Technology in 2006. After that, he did postdoc research at both Fortec and National NSLS. Before joining SSIL. And Dr. Lee is specialized in the soft X-ray spectroscopy study as well as the soft X-ray scattering. And he took the initiative effort, developed the first random soft X-ray scattering technique at SSIL. So today he's going to tell us the story about the spin, and he's going to mostly focus on the so-called emergent phenomena on the oxide interface. Let's welcome him for the lecture. Thank you. Can you hear me? Okay. I'm Jim Lee. I'm the staff scientist at SSIL. So today I'm very happy to give my role to SLAC paper. So my supervisor introduced me to using a very nice, very fancy words, but it's too difficult if you heard emergent, oxide, and spin, everything. It's very difficult word. So title-wise, oxide spin, also I was surprised to make a title like that. So how do I explain my talk? I practiced with my wife, and I introduced my presentation, and I want to convince my wife can understand my talk or not. I'll say it. So she, what the hell? She doesn't understand what I'm saying. So I'm just to change again my presentation to give an essential story to you guys, because this is